Hello everyone, so good afternoon. I'm going to talk about what we call fuel recycling and molten salt reactor, a game changer for sustainable energy future. That's the topic. Okay guys, have you ever seen such a piece of glass? Do you know what it is? Okay, that's natural glass, actually. That glass is exactly the same kind of glass you could find, for instance, near the Etna volcano in Sicily, right? That piece of glass is a kind of byproduct of a lava. That's natural. Otherwise, the man wouldn't, or the woman wouldn't handle it. But did you know that that kind of glass is also used in the nuclear industry? Roughly the same features, roughly the same characteristics. Actually, it is used in the recycling nuclear industry to immobilize fission products in what we call minor actinides. Okay, it's some of explanation for you guys. So fission products is something we can get out of the reprocessing process at La Hague site, for instance, in France. It's something not reusable. It's a very radioactive material, as well as minor actinides. So what we've been doing for years at Orano La Hague site, is to immobilize those products in the same kind of glass. It's a very sustainable, with a very long life duration, so you can put it in what we call geological disposal facility for hundreds of years. It's going to stay stable from a chemistry standpoint, from a physics standpoint. So now you guys are wondering, what's the connection? What's the link between that piece of glass and molten salt reactor? So that's the story I'm going to tell you now. By the way, my name is Olivier Drouveau. I've been working at Orano for 30 years plus, roughly speaking, both in operations, in the beginning of my career at La Hague site, many years in the vitification process. That's why I'm emphasizing on vitification. And I shifted to project management in France and abroad. That's why I've got this weird accent from the US or UK or South African. So US, UK, Japan, and then I came back to R&D 10 years ago. Okay, so now we're going to speak a little bit more about the molten salt reactor. Orano is not a specialist for molten salt reactor, but I'm going to explain later on why we're exploring this path. The molten salt reactor is what we call a generation 4 advanced reactor. Okay? It means that it's not deployed yet, but many people around the world are seriously looking at this because we expect many assets from this technology. So before dive into the principle of a molten salt reactor, the first basic I need to recollect for you guys is about the current nuclear power plants principles. So the current nuclear power plants use what we call chain reaction. Chain reaction, they use fission. In other words, in simple terms, we use radioactive materials such as uranium-235, fissile materials, so that you can split the core of the atoms in two parts, thanks to the neutrons. And then when you do that, you're going to split them in two parts. You're going to release a big amount of energy and several other neutrons. That's the fission principle. So it's been used in the current nuclear power plants for years. That's the generation 3 power plants. The molten salt reactor will still use fission. It's not a fusion reactor. It's fission. The difference between the current nuclear power plants and that baby is the fuel is a salt, is liquid, whereas in the current nuclear power plants you have solid fuels, ROS, with uranium oxide, enriched with U-235. That's not the case. Here you have the fuel is liquid. It's a salt, molten salt. And it contains it can contain many kind of nuclear materials, such as uranium, enriched uranium, thorium, plutonium, and even minor actinides. So you begin to understand now why I'm talking about vitrification first. Okay? That baby use any kind of, can use on paper a broad range of nuclear radionuclides, sorry. Apart from that, it's roughly the same principles. In the reactor, you have what we call criticality, and it releases a huge amount of energy. Then through heat exchanger, you recollect that energy in an intermediate circuit, and then you can power up turbines or even produce directly steam. When we say it's a very flexible technology, we just mean that the expectations is to use it for different configurations. Either you can use it in what we call thermal spectrum. It means that the neutron, even though they are fast, they are not that fast, and they're not that energy. And you can use it in fast spectrum with a much more neutron energy, very fast velocity of neutrons. You can also, as I've just said, use it for different kind of fuel, and that's the flexibility. Another asset of this brand new technology is what we call inherent or intrinsic safety concept. Why is that? If you take the current nuclear power plants, what we call the pressurized water reactors, you need to use what we call a moderator, which is pressurized water, and the water is both the moderator and the coolant. In this case, it's different. The fuel is, as I said, is a liquid, a molten salt, and it's both the fuel and the coolant. You don't need any moderator. You can moderate with graphite if you will, but you don't need moderator. It's much simple. The good news is, if you were to overheat the baby inside, you're going to have liquid expansion. And the critical smart guy is going to tell you, okay, if you've got liquid expansion, you're going to shut down criticality. It's going to be controlled. No worries. Okay. So in other words, it's a kind of auto-controlled safety. If you overheat, you shut down the criticality reaction. If you underheat, you reignite the reaction. Sounds good, doesn't it? Okay, so that's inherent safety concept. Another asset of this technology is the one we call high energy density. If you so just a few figures. By the way, as you may have noticed, I don't have many figures, neither words on my slide. So I need to remember everything. So energy density, what does it mean? If you take two figures, the current nuclear power plant's generation, you're going to have, roughly speaking, around 100 and 200 megawatt thermal per cubic meter. Okay, 100 to 2000 to 200. Whereas for the baby here, you're going to have more than 250. So in other words, you don't need a big baby, a big size. You can have a compact capacity. And if you look, if you think about this, a capacity means you can manufacture a reactor and then put it on site. You don't need big nuclear power plants to be built on site. That's an asset. Less cost expected. Another asset is about what we call high operations responsiveness. So just to understand that point is to come back to the neutronics kind of basics. I'm just trying to explain. I'm not a neutronian, by the way. I'm just trying to explain. Okay, so what it means is that that kind of technology can respond very rapidly. If you need to get power on the grid, you can respond within second-ish. Whereas if you take big nuclear power plants, the current generation, it's not that fast. So the explanation, the real scientific explanation is a little bit complicated for me, but in a nutshell, it has to come back to the liquid fuel properties, the expansion, and the other way if you were solidified. So both way will release many energy or will retain energy. So it's a kind of auto control, if you will. And that property is pretty cool because if you imagine the deployment of such nuclear power plants with molten salt reactors technology, you can say, okay, I can have big nuclear power plants like for instance, the sodium fast reactor, big energy, big watts, and next to that you can have a small fleet of molten salt reactors, so you can adapt to the load of the grid. Another asset, I will talk about the drawbacks afterwards, okay? Don't worry. Another asset is about a better energy effectiveness. It's just a question of physics. You operate the baby at a higher temperature. If you compare to the current nuclear power plants, the temperature of the pressurized water is about between let's say 200 and 300 C. Whereas for this technology, you can, because it's molten salt, it's between 500 and 800 C. So therefore, from a physical standpoint, you're going to have a much better ratio between the megawatt thermal and the megawatt electric. Okay. If I want to give you a figure, the current ratio is 40%, roughly speaking. You could expect up to 50%. That's interesting. Okay. All that being said, why on earth Orano is exploring MSR? Because I've been talking for 5 minutes about, okay, the MSR, blah, blah, blah. But why are we exploring this path? Mainly for two reasons. Because Orano, as you might know, has many activities. And among those activities, we've been recycling spent fuel for years. But spent fuel from the current generation. So we've been used at doing that at industrial level. And when we heard about this technology, we said, okay, this could enhance the fuel recycling capability. So we need to be part of that game. On top of that, relating to the wide spectrum capability and the ability to use plutonium, thorium, minor actinides, we say, okay, we could burn some waste in it, such as minor actinides. So we could fuel MSR with waste. That's why we're exploring that path. Okay, so just bear in mind what's the current situation as far as the final waste disposition. The rationale is, okay, as far as the final waste disposition, we're going to store final waste, meaning the waste with the fission products and monoactinides, in a glass, the one I show you a few minutes before, and we are going to store that in what's called a GDF, geological disposal facility. So hundreds of yards under the Earth's surface. So you can see those two guys walking around in Cigéo. It's in France. Okay, it's a prototype, but it's a big baby. A big facility, underground. So the rationale is to say, okay, final waste without long-lived radioactive material, that's good, because it means much less radiotoxicity in GDF. Just to give you a figure, or two figures. Well, currently, if you want to decay fission products and monoactinides in this kind of facility, it requires at least 10,000 years. 10,000 years. Okay? If you get rid of those monoactinides, so, by the way, they've got names. Americium, neptunium, and the cousin called curium. German cousin. So if you get rid of those guys, you're gonna go down to 300 years. 300 years versus 10,000 years. That's the benefit we're expecting. So there's no figures on my slide, but you can check it out. Okay, so now what can we do Orano-wise to speed up that exploration? What's the rationale? So what's going on in the world now is we've got many startups and developers studying the MSR reactors. Our job is to accompany those guys and to provide them with fuel. That's the thing we're going to do. We could do that because, guess what? We've been reprocessing spent fuel with chemical processes at like for several decades. So we are chemists, specialists, if you will, at industrial scale. Sounds good. So what we're going to do is what we are already doing is we're implementing R&D programs to synthesize and purify salt out of plutonium, so PuCl3, for instance. And the good news is that we are halfway to do it, because within the current facilities, we've got some processes relevant to do that already. We just need to add some new bricks to have this PuCl3, for instance. And by the way, just something you have to bear in mind is we need to produce purified PuCl3, because if we were to do PuCl3 with some oxygen and hydrogen, we would have a thermalized spectrum. No way, we want a fast spectrum, so we want purified salt. But the good news is we have the skills, we have already a big site, and we've been doing reprocessing for 30 years plus, industrial scale. And another good news is that within Orano, we've got another BU called Nucléaire NPS, so standing for Nuclear. Thank you. I've got some good fellows from Orano around. Nuclear packages and services. In other words, the guys that are designing casks and operating casks. So we've got the competency, the skills to have the proper cask to transport that salt to the first prototype of molten salt reactor. So that's why we're really interested in this endeavor, because we have the skills, we have industrial skills, we have lessons learned, and we have the will, the willingness to accompany and to keep doing R&D, as we speak, to go down that path. Okay, and the final slide is about just to re-say something I've just said earlier, is that currently many MSR developers are around. There's an ecosystem. Our goal is to partner with some of them, targeting a first MSR demonstrator in PuCr3 to be commissioned in the early 30s, roughly speaking. Thank you very much.